All right, welcome back. So we just talked about an elevator and acceleration relations. So I'm going to talk just a little bit more about that. Let's take a case where you're in some kind of, you're in some kind of, well, we have a person, some kind of vehicle. Tell you what I'm going to say is we're going to have an airplane, and I'm drawing this airplane vertically for a reason, which you'll see in a minute. So there's our airplane. Inside the airplane is Tom Hanks. So I'll put a little T for Tom Hanks by his feet. There's A for airplane. And then down here is ground. And the airplane flies through an arc, a parabolic arc, and such that the airplane's acceleration, I'm going to do this with vectors now, the acceleration of the airplane with respect to the ground. Just to keep my letters absolutely straight, what I'm going to do is use P for plane instead of A for airplane, because I'm using, there we go, because I'm using A for acceleration. I don't want to get confused. So the acceleration of the plane with respect to the ground is negative g j hat. And we're going to say that there's a y axis there and an x axis there. But this is just a vector acceleration downward due to gravity. The acceleration of the plane, the plane is going through a parabolic arc, and the pilot actually has to do some fancy tricks to make it behave like this, but it can be done. And I'll explain when and where it's done in just a minute. If you haven't already figured this out, you may know what I'm talking about already. Meanwhile, Tom Hanks is, in the middle of the cargo bay of this airplane. He's not near the walls. And the acceleration of Tom Hanks with respect to the ground, which I'm going to denote ATG, is negative g times j hat. That's just gravity pulling on him, right? So what then, we ask, is the acceleration of Tom Hanks with respect to the plane equals what? So let's make an equation with these three, and we can look at our subscripts because we've been careful with our notation. We can look at our subscripts and see which ones fit. So let's go with orange here. So acceleration of Tom Hanks with respect to the plane, acceleration of the plane with respect to the ground, and acceleration of Tom Hanks with respect to the ground. Well, TP, PG, we can put those together and smash the P's out in the middle to get TG, so that's how it works. So acceleration of Tom Hanks with respect to the plane plus the acceleration of the plane with respect to the ground equals the acceleration of Tom Hanks with respect to the ground. Whoops, or not G. G, there we go. All right. Tom Hanks, I'm writing TH, that's why I'm getting confused. Okay, so acceleration of Tom Hanks with respect to the plane, acceleration of plane with respect to the ground is negative g j hat, and the acceleration of Tom Hanks with respect to the ground is negative g j hat. Well, lo and behold, I'm going to go through this like teal looking color, negative g times j hat and negative g times j hat, those cancel out, and what we're left with is the acceleration of Tom Hanks relative to the plane is 0. What this means is that Tom Hanks, if he's in the middle of the plane, he'll just float there in the middle of the plane. If he is, kicks off from one wall, so let's, zoom in on Tom Hanks with respect to the plane. If he kicks himself off from one wall with his foot, say, he'll just go cruising across. If he's floating in the middle, that'll happen. And the last question, to go with this example, is what movie is Tom Hanks filming? And the answer, it's not Castaway, which some of my students guessed, but no, it's not Castaway. The answer to what movie is he filming, the answer is Apollo 13. The reason why is because this is how they film scenes that take place in space where the astronauts have no acceleration relative to their ship. So this is how they film the scenes where Tom Hanks and Gary Sinise and whoever the other guy was it Kevin Bacon, I think? Yeah, something like that. Those three were playing the astronauts of Apollo 13 on their way to and from the moon, as they tried to save their asses, save themselves from dying of starvation and all. So here's so people think of being in space as experiencing zero gravity, but that's not true. What it actually is you're in something called free fall. And to understand why, let me show you what's going on here. So here's, in a normal trip to the moon, say, here's the Earth, okay, and here's the moon, and your spaceship here is somewhere in the middle, and here's the astronauts inside, whatever. Okay, so the astronaut will label A. We'll label the space capsule C, and then we can put some reference frame, I guess. We call this like a space reference frame or whatever, so S or whatever. And so the acceleration of the capsule with respect to, well, so the question is there gravity affecting these things? And yes, there is. The Earth is pulling on the space capsule. The moon is pulling on the space capsule. I mean, they're between the Earth and the moon, and the Earth keeps the moon in orbit through gravity, right? So obviously, if gravity can reach that far, then it can reach, just far enough to get to the capsule, and the moon's gravity can reach the capsule too. So what's really happening is the capsule has some acceleration with respect to, inertial space. So we're going to write not equal to 0. But the astronauts are also accelerating. So acceleration of the astronauts with respect to this inertial space is not equal to 0. Well, how do their accelerations relate? Here's the thing. If the acceleration due to gravity on an object, so acceleration due to gravity on one object is proportional to the mass of the object attracting. So gravitational acceleration from Earth is proportional to, well, I'm just going to do this, squiggly proportional to the mass of the Earth divided by the distance to the Earth squared. And so basically for this capsule and for the astronauts, it's the same distance, right? So any acceleration the capsule is feeling towards Earth, the astronauts are also feeling. If the moon is accelerating them, then they're also feeling that. So the point here is that the acceleration of the capsule with respect to space equals the acceleration of the astronauts with respect to space. And, what does that mean then for the acceleration of the astronauts with respect to the capsule? Well, astronauts with respect to the capsule, they're both accelerating the same. So the acceleration of the astronauts relative to their space capsule is 0. And that is why, that they can float around inside and not be pulled to the walls or pulled to some floor by gravity, because any acceleration they're getting from gravity, their capsule is also getting from gravity. So one thing this means is that if they were they were here in orbit, so they're orbiting like that. Dang, there we go. Okay, they'd be feeling some acceleration there, and the capsule would be feeling some acceleration. They'd feel 0 relative acceleration. But if they're just sitting here, and the capsule's feeling some acceleration, and they're feeling some acceleration, either way, they're not going to feel any relative acceleration in the capsule. But here they're in orbit, and they've got some velocity here that's going to get them going around. Here, if they don't have any of that sideways velocity, they're just going to go and crash. So the interesting thing is that falling to your doom when your capsule is crashing won't actually feel any different to you than orbiting. You can't tell the difference just with your inner ear and your senses and stuff. That's why you need instruments and telescopes, and you need to be looking out the window, that kind of thing. So anyway, that's the end of interesting adventures with relative motion acceleration.